So Liz, this is it, right? The hockey puck's hitting, moving east.
Yeah, no, when they said definitely stone them, I'm getting it.
So
Then no matter what happens,
by being an elastic collision,
by us.
we know for sure that momentum and kinetic energy are conserved.
Whenever I try to set up the equation, it'll always want to go.
Right, but you're gonna set up two equations, right?
Okay.
Yeah. So we're gonna go.
Okay, never mind. I'm good then. That's all I needed. Sorry.
That's so
I
far.
can see it.
Yeah. So what are the two equations? Then?
It's 1/2 of v squared and then all equals. So it's usually 2, 1/2 of v squared, and then go 1, and then
You got it. Yep. And this one is linear,
okay.
non-two-dimensional, it's one-dimensional. So.
Okay. I just tried to. I like to.
So this one is that it's using the fact that the change in the momentum is the impulse, which is force times time. So the delta t, so in each of these cases you have the force and you have the delta time. For me it's 3 seconds. So in the I case, it would be, for me it'd be 28 newtons times 3.0 seconds, which would give me, what, 84 newton seconds, I think. And in the J case, J direction, that would be -10.
Wait, why would you multiply by 7 in the first one? You don't have a time. For the 28. It's only 28.
Oh, okay. So, sorry, I missed the t squared when I looked at it originally. I thought they were just giving our force as the two components of it. So what you want to use is our more advanced. Let's grab our equation sheet just so we have that. Let's see. Oops. So my pen out. So, because our force is time dependent, which I missed, the impulse is going to be the integral of the force dt, which will be the, so same idea except we don't have a constant force. So we can kind of get rid of this part, and we're going to use that the impulse is the integral of force dt. And we're going to integrate that from 2 to 5. Okay? So the integral of this, we can think of it separately. The integral of 28 I minus 10 t squared j, all dt, can be broken into the integral of 28 dt I plus the integral of -10 t squared dt j. Since they're perpendicular to each other, they don't affect each other. And here you get 28, and each of these is from 2 to 5. Sorry, I dropped that. So you get 28t I, and you get minus 30 t cubed j, evaluated from 2 to 5. Right? And you actually can think of each of these as evaluated separately. You don't think of them as combined. Okay? And then, of course, change is final minus initial, yeah. No, because when I take the derivative of this, the 3 comes down. Right? Oh, that's right. Yeah. Yep. Yeah, I did it the reverse way, sorry. And then you substitute it, right? So you get 28 times 5 minus 28 times 2. All of that is your I component, and your J component is negative 10 over 3, 5 cubed, plus 10 over 3, 2 cubed, and that's your J component. Chloe, is that good?
Yeah.
Yeah, so 20, the two objects have equal mass, and since it's completely inelastic, afterwards they're going to have there'll be one object of double the mass.
Oh, okay.
So for the momentum, one way to think about it is momentum of object 1 ahead of time. I'm picking an arbitrary angle here, okay? Momentum of object 2 ahead of time. Those two are going to combine.
Yeah.
And actually, we should really, yeah. And this will be the momentum of object 3, let's say. Now, the thing to be careful of is while these are in the same direction of their velocities, the velocities would not form a triangle like this. So you can't just cancel out all the masses completely. You can, because here you have m v1, here you have m v2, and here you have 2m v3.
Yeah.
You can eliminate the m's because they're just a scaling factor. But the temptation is to say, oh look, v1, v2 equals v3, and that doesn't work. The directions work, but v3 is going to be short of making the triangle. You know how v3 is related. So these actually, we can bring these to v's, right? Get rid of the m's.
Yeah.
And replace this. We have to keep that 2. But now v is v over 2. In my case.
Oh, yeah.
Right? And so now I start looking at, oh, wait a minute. I have, for me, it's an equilateral triangle. I've got VVV. But there's going to be a humor. But then it's just trig.
Yeah, okay.
But realize that the angle you want is that angle.
That one, okay.
Because that's the angle between the two initial velocities.
Yeah. If it wasn't like mine, I don't think it would be such a perfect equal triangle. Are you do like log sines and stuff, log cosines?
Yeah. Yeah, because you're not going to have a right triangle. Yeah, so I would do law of cosines to find this angle, and then my answer is 180 minus that.
Okay.
Yeah.
Cool. Thank you.
Yeah. All right, so number 2. I'm going to sketch myself a little axis here. I'm going to need that. Baseball is moving along the x-axis. So it's moving this way. Speed of this. Strikes the fence at an angle of 45 degrees and rebounds. Oh, okay. So then my fence. Here's my fence, and then it rebounds like that. So this is momentum initial This is momentum final, right? So in the I direction, my impulse is going to have to be in this direction and equal to whatever my initial impulse was, initial momentum was, because I have no momentum left in the x direction. And then in the y direction, my impulse is going to have to be in this direction, and it's going to have to be equal to whatever that is. So so Jx should be 0.162 kilograms times 25, and that should also be, but that's going to be negative, and then I should have that positive same value for in the y direction. Let me try it, see if it works.